So in this video we are going to look at an example problem. We might look at another one depending on how long this video gets to be. So you might want to also pause the video and sketch the circuit out. I'm just going to proceed as if we all have the circuit sketched in our notes. Now the problem tells us here that it is known that I1 is equal to 10 amps and I2 is equal to 25 amps. And then we're supposed to do two things here. We're supposed to find the power supplied by each source and part B here is we're supposed to show that the total power supplied equals the total power absorbed. We know that it should, but we're supposed to show it. If I could spell absorbed correctly. Okay, so what I'm going to do here with this picture right now is instead of having this be I1, since it tells me that that's I1, I'm going to put this right here and put 10 amps going down that branch there. And then I'm also going to remove that one here and again here put that this is 25 amps. And then we're going to have to apply both KVL and KCL is my guess. I don't know, I haven't done this problem yet, to get everything we need. Because in order to determine the power supplied by each current source, what we need to do is we need to find, and I'll call this just IA, and then we also have to find this current IB, because then the power supplied for A would be simply 130 times IA. It'll be negative because the arrow is hitting the negative side of it. And then for IB, it would be power for B would be again the arrow hitting the negative side, so it would be negative 460 times IB for the power. And these would be negatives, and again, because they're delivering power anyway. So we'd have to figure out what IA and IB are. So there are multiple ways to approach this problem to get an answer here for us. One thing we can do here is I can see here, and I'm going to probably draw on this picture and erase here. If I look at this node right here, because I'm trying to do things with as fewest number of unknowns as possible, I can see that I have 10 amps coming into this node and then 25 amps leaving going down here. Now, if I have 10 amps coming in and 25 amps leaving, that means I also have to have some additional current coming in, and I'll just call this I3 for now. And using KCL, we know that 10 plus I3 has to equal 25 amps, of course, and so we get that I3 is equal to, sorry there, couldn't do arithmetic for a second, 15 amps. So now I'm going to redraw this here a little bit and put it over the resistor here, so we've got 15 amps. Now if I were to look at this node right now, I see that 15 amps is leaving that node, IB is coming into that node, and IA is leaving it. So I still have two unknowns at that point. So it doesn't necessarily look like that would be a good node to tackle next. And if you look at the other nodes, we're going to run into the same problem. If I look at this node, well, I've got IA coming into it, 10 amps leaving it, but then I'd have some other current coming this way as well. And then I'm going to run into the same thing here. You know, I got 25 amps coming into the node, but I don't know what this current is coming in or what this current is if it's coming in or leaving. I don't know what those are. So I found one piece of information here, and we're going to need to find all these pieces of information because part B, I'm going to need to know at least the current or voltage across every resistor in order to compute the power of the resistors. So let's think of something else here we could do here, and I'm going to do this one in green here because, again, there's several approaches we could take to this problem. First thing I'm going to notice here is I could draw a loop right here right now for voltages here. And now I'm going to go ahead and write the equation down here that we'd wind up getting, but I'm going to write it in terms of voltages. So we'd wind up coming in on the negative side, negative 460 volts, and then I'd say plus, it's going to be plus here, this voltage across 10 ohm, and I'm going to say just number 1 because that's this first 10 ohm resistor here, plus the voltage across the 10 ohm resistor number 2, because that would be the second one here, plus the voltage across the 2 ohm resistor. And we know that that's all equal to 0. Well, how could this possibly be helpful to us? Well, this is again where we want to remember Ohm's law as well. So we're combining all things here together. We're combining KVL, KCL, and Ohm's law. We know from Ohm's law that voltage is equal to current times resistance. And well, if I look at this here, I don't want to mess up my diagram too much here, this 10 ohm resistor here, I know that there's 15 amps going through it, so I know that the voltage for 10 ohm number 1 is equal to 15 amps times 10 ohms, which gets me 150 volts. Now I can do the same thing for the second 10 ohm because I know there's 25 amps going through this second 10 ohm resistor. So I can say V 10 ohm, the second one, is equal to, well, I've got 25 amps going through it times 10 ohms, which would be 250 volts. And so now I wind up with getting an equation. I have negative 460 volts plus, here I'd have 150 volts plus 250 volts plus the voltage across the 2 ohm resistor, and that's all equal to 0. Now from this, of course, again, we have one equation with one unknown now. It's very simple to solve this, and we can see that the voltage across the 2 ohm resistor is going to simply be 60 volts. So we now know that this voltage here, plus minus, is 60 volts. Well, how is that useful to us? Well, I'm going to erase this green little arrow here. I'm going to draw in a real red here, and I'm going to say the current through the 2 ohm resistor. Well, I know the current through that 2 ohm resistor now. The current through the 2 ohm resistor, just using Ohm's law again, the current through the 2 ohm resistor would be the voltage of the 2 ohm resistor, of course, divided by the resistance. So if we did that, we get voltage of the 2 ohm resistor, and then that is equal to, well, I'm sorry, current of the 2 ohm resistor is equal to the voltage is 60, and then divided by 2, which is 30 amps. So I have now that this is 30 amps, and I'm making a lot of good progress here. Why am I making good progress here? Well, let's look at another node here. This node is a trivial node. I've got 30 amps coming into the node, and I have IB leaving the node. So I have right now what IB is, because 30 amps is entering the node. There's no other places for this node to go. IB is leaving the node. So I have then that IB is equal to 30 amps. Now that can give me the power for one of my problems right now. And again, it's a negative because what side of the voltage source am I hitting with this arrow? The negative. So in other words, if you want to think about it, power is, well, the voltage source is 460 volts, negative, because I'm hitting the negative side of that voltage supply. Because remember, whenever we have the arrows, if it hits the negative side, we put a negative and then the value of the voltage supply, times the current, which is 30 amps. And I'm going to go ahead and use my calculator on this so I don't make a silly arithmetic mistake. And we get negative 13.8, and I'm using engineering notation here, kilowatts. So which of course is a lot of power, but the values here again that we've picked in this problem are chosen to make it easier for computations. Now we've actually really made ourselves a progress, because part A, we're supposed to find the power supplied by each source. Well, we found the power supplied by this source right here. We just need to do it for the 130. And we know to do it for the 130, I need to know what IA is. Well, let's look back at where we're at right now. I can erase this IB because I know what that current is. It's not IB anymore. We know that that current here is 30 amps. Now let's reevaluate this node right here. If I reevaluate this node, I can see that I've got 30 amps coming into it, 15 amps leaving to the right, and then I've got IA leaving it going up. So I would have, for the current, I'd have that current entering is 30, and then the current is leaving is 15 plus IA, which gets me IA is 15 amps. And now we can get the power supplied for, this should be for B, for source A. And again, look at where the arrow is coming. So we know that IA is now 15 amps. IA is coming in on the negative side, so that means I'm going to have negative 130, because it's the negative and then the value of the voltage source, times the current, which is 15 amps. And again, I'll use my calculator to do this. And I get negative 1.95 kilowatts. So that's the power being supplied by each power source. And we know it's being supplied because, again, I'm getting negative values. So let me just put here the total supplied is, again, not trusting my arithmetic skills here, using my calculator, would be 15.75 kilowatts. Put the little negative there. So now part B on this is that we're supposed to show that the total supplied equals the total absorbed. So in order to find that it's equal to the total absorbed, I need to find the actual power across each resistor. Now this is not going to be as hard as it sounds, because we've already got a lot of the information we need here. We just have one other piece of information that we need. We have the current through every single resistor, including this 2 ohm resistor up here, because I've got 15 amps coming up, so that means I've got 15 amps going through this resistor here. But the only current that I don't know is the current coming down through this 100 ohm. But now I can look at several different nodes here. I could look at this node, or I could look at this node. And if I look at this node, I'm not even going to write the equation down. We can probably just see this in the head. I've got 15 amps coming into the node, 10 amps coming down here, which means I have to have 5 amps coming off of that, because I've got 15 entering and I have to have a total of 15 leaving. So that means there's 5 amps going through this 100 ohm resistor. And so we also could have done it down here, where we would have had, we can see it still works for this node as well. I'd have 25 and 5 amps coming in, which of course that's 30 amps, and then I also have 30 amps leaving. So we could have used either node. And in both cases we get 5 amps going through that 1 ohm resistor. But now remember, because we're dealing with resistors, we don't need to do voltage times current is equal to power. We can use power is equal to I squared times resistance, or power is voltage squared divided by resistance. And clearly the one we're going to want to use is this one right here, because we have the current through every single one of those resistors. So let's go back up to the diagram. I know we're going up a little bit here. I'll call this 2 ohm resistor resistor 1, just like we called this one resistor 1, this one resistor 2, and then we'll call this 2 ohm resistor resistor 2. So the power for 2 ohm resistor 1, well, the current going through that is 15 amps. So I'd have 15 squared times the resistance, which is 2 ohms. And again, just using calculator to do this computation, we get 450 watts. And again, it's positive, and it should always be positive, because remember, resistors can only absorb power. All right, so let's look at the power across the 2 ohm resistor, that's number 2. And so the number 2 ohm resistor was the one down here at the bottom. 30 amps is going through that. So 30 amps squared times 2. Don't make a silly mistake saying, oh, well, the current's doubled, so the power's doubled. No, you're squaring that number. So in fact, it should be 4 times bigger. So you have 30 squared times 2, and you get 1.8 kilowatts, which is 4 times bigger than 450 watts. As a side note, we could write 400 and, whoops, my screen just went blank there for a second. We could write, sorry, the video kind of went a little weird there. We could write 450 as 0.45 kilowatts. So sorry about the little flickering there. I'm going to go back here a second. What happened is my tablet was running out of power. And so what I was saying is, instead of writing 450 watts up here, we could have written this as 0.45 kilowatts. Then moving on, we have the power for the 10 ohm resistor, number 1. And if I scroll back up here, I can see that the 10 ohm has 15 amps going through it. So I'd have that this is equal to 15 squared times 10, which again, using my calculator, I get that this is 2.25 kilowatts. And then the second 10 ohm resistor has 25 amps going through it. So that would be 25 squared times 10. Which is equal to 6.25 kilowatts. And then we have the power across the 25 ohm resistor. And that's 10 amps going through that. So this would be 10 squared times 25, which is 2.5 kilowatts. And then finally we have the 100 ohm resistor, which has 5 amps going through it. Which would be 5 squared times 100, which should be 2.5 kilowatts. Let me just double check again. 2.5 kilowatts. So that's the power in each one of these resistors. Now, if I just sum all of these up, and this is why I converted the first one instead of 450 watts to 0.45 kilowatts, because you need everything to be in the same units here. So I could just do 0.45 now, plus 1.8, plus 2.25, plus 6.25, plus 2.5, plus 2.5. And when I do that, I get 15.75 kilowatts. And we can see, yes, the power absorbed by the resistors is the power being supplied by the power supply. Now, obviously this video went a little bit longer, but this is a good example problem. I encourage you to even redo the example problem without looking at the video, redo this problem. I will do another example using KVL and KCL here before we move on to some new topics.